Next, we're going to talk about x-rays and how they're actually made in particularly a medical setting. X-rays are produced by stars, just like every other spectrum of electromagnetic radiation, but how do we safely produce x-rays for your dentist's office or for your doctor's office? So x-rays were discovered by Röntgen in 1895 and identified this as an electromagnetic radiation with a very short wavelength. Wavelengths were less than ultraviolet. Wavelengths are typically around 0.1 nanometers, and x-rays are able to penetrate most materials with relative ease, which is why we use them for imaging, because we get a different amount of penetration for dense material like bones versus soft material like tissue. So how are x-rays actually made in an office type piece of equipment that you might see in your doctor's office or in your x-ray lab at a hospital or doctor's offices? X-rays are produced when high-speed electrons are suddenly slowed down. So most of the time in classical mechanics, we think of when something slows down, you need to produce heat. When you slow your car down, you produce heat on your brake pads. When you slow down from running, you produce heat in your muscles. So in the big world, we produce heat, and we just saw that heat is really electromagnetic radiation, or can be a form of electromagnetic radiation. So electrons give off their energy in the form of electromagnetic radiation, and there's a lot of energy if they're moving fast, and so they produce very high energy electromagnetic radiation, or x-rays. So here we have this machine that, remember, electrons flow in the opposite direction. So here I have my electrons coming out of this high voltage source and being produced in this filament. This filament is basically a lot like your light filament, the electrical element on your stove that emits electrons. So this is an electron emitter. Then these electrons hit this copper rod and we emit x-rays. So here goes my electrons, and here are my x-rays coming off. The heat generated by the current in the filament causes those electrons to be emitted, and the free electrons go towards the metal. So what's happening is that as this electron slows down, if it curves around the nucleus of the atom, as it's being captured, it emits the electron. And these electrons are then recycled back through our energy source. And so as this deceleration happens, we get this photon. This photon has energy HF. So we're talking about really as an energy of balance, that here we're talking about the change in kinetic energy of the electron is the energy imparted to this photon as it leaves. And remember that the energy that we change, the kinetic energy change of the electron is equal to its change in potential energy. So we would say that would be a change in potential energy. Potential energy for a charged particle is equal to V times Q. And often in these we're going to use electron volts, which is basically the amount of energy change that one electron goes through. If it goes through 1 volt of change, it's just a nice convenient number for use for particularly small things. So here we have our change in energy of our electron is equal then to the change in energy, or the energy imparted to our photon. So not all energy is produced at this wavelength, but this is going to be the most energy produced. So here we have a cutoff frequency for an X-ray tube is 46 kiloelectron volts, and we want to figure out what the frequency is. So we're given this is 46, and we're going to use H in electron volts just to make our life easier. So this is 46 times 10 to the third electron volts divided by 64.136 times 10 to the negative 15th electron volt seconds. Gives us the answer of 1.1 times 10 to the 19th hertz.